We good to start? Okay. Okay. Thank you for coming and for supporting me in my tutorial ideas. So I think this is going to be a strange class. This is what I planned. The first hour with a demo, introduction, some basic concepts, and then the remaining 2 hours, I'm going to show you this actual project, how I developed it. So it's going to be mostly, or actually all of it, lecture type. You don't have to do what I do if you don't want to. If you prefer to pay attention, that's totally fine, because the project is on GitHub. It's yours to keep. You can play with it some other day. They asked me to share that link, which is how you are going to rate this class when it's done. So that's important, because they show me that, and then I can improve the one I do next year. So I think we are going to get into it. So the project that I developed for this class, it's called Microflask. It's based on the project that I did last year, which was called Flask, just Flask. So I assume a lot of you are interested in migrating an existing application to microservices. I assume that's why you're here, at least most of you. So I'm going to show you how you can do that. So I basically sat down and converted Flask to a microservices architecture, and basically that's going to be the 2 hours. I'm going to show you how I did that. The end result sits in not 1, not 2, but 7 GitHub repositories. So we have 7. This is important. If you go look tutorials up on YouTube or GitHub, whatever, at least most of the ones I've seen, they use 1 repository, and then they put directories for the services, and that's probably not a good idea. I mean, on a real situation, you would probably want separate repositories for each service. So that's what I did. I did that way here. The project runs on Python 3. This is the first time I feel confident that I'm not going to get too many of you upset because I didn't test on Python 2. Yes? Good. Well, that said, the only thing I didn't do is test it. But I mean, I'm sure there might be little things here and there, but it should totally run on Python 2.7 if you wish to do that. Don't see why you would at this point, but anyway. It also uses Docker. So I'm going to explain why I decided to go with Docker for that. And also decided not to use any of the platforms that are popular as for hosting microservices. So no AWS, no Kubernetes, nothing like that. I built it all myself in a true Flask spirit of keeping things simple. Because I think even though you will probably use one of those platforms when you develop your real projects, my idea here is to teach you how microservices work. And I'm very proud to say that the platform that I built is written in Python and Bash. So no Go, none of the shiny new things that are difficult for a lot of people. This is all Python and Bash. So okay. Before I get into the first portion, I want to make sure that all of you know that you can run this on your laptop. The project runs in a Vagrant virtual machine. You need VirtualBox and Vagrant installed. So I sent an email telling you the instructions. If any of you have problems, I don't think I'm going to have time during the class to help you, but I'm totally cool with helping you during the break or after class. So come find me. Yes, question. So you can find it in the class website, I think, in the PyCon website. No. Okay. So go ahead and take a picture of this if you want, and then after class I'm going to publish this. So I'm going to tweet the link to the slides. But basically, you need to clone microflag admin. That's one of the 7 repositories, the one with all the the scripts. And then just say Vagrant up on that repository, and that will create the VM. The VM will be a 1.5 gig VM, so it's fairly small. Should work if you have a 4 gig or higher laptop, but recommend 8. This machine that I have here, this is the machine I take to all my presentations. I bought it in 2011, and it runs this no problem. It's totally fine with it. So it's a very old machine, and still can do it. On Windows machine, there might be, sometimes you need to tweak the setup to get VMs to work. So if you need help with that, let me know after class. I'm happy to help you. So this is a list of the basic Vagrant commands that you are going to use when dealing with this VM. You're going to see me use some of these. One that's actually a very good idea, after you get the Vagrant up, for the first time, that's going to run for maybe 20 minutes. It takes a lot of time to install Docker, actually. So it'll take about 20 minutes. After you're done, you can do the snapshot. So Vagrant snapshot save, and then give it a name. I used clean. And that's so that if you then mess it up, you don't have to reinstall the whole thing again. You can restore the snapshot. That's actually what I did myself to play with this a lot, so that I don't have to wait all those 20 minutes. So anyway, anybody, any questions about this? Good. So this is Flask, the project that I did last year. The green boxes are the services of the application, and then we have storage in orange and the load balancer in yellow. So it looks like it's pretty simple, right? I mean, I don't think it's simple. And the reason why it looks simple is that because all the complexity is in the 2 green boxes, right? So these 2 boxes, the way I left it in the previous class, they were scalable. So you could run a bunch of Flask instances behind the load balancer, and then you could also run a bunch of salary workers, right? It was freely scalable. You could scale both separately as you needed. And then there was a database, and there was a message queue that we used for the WebSocket portion of this application. So today we're going to transition that into this. And there's a bunch of new things here. So we start with 5 green boxes. Those are the 5 microservices that we're going to use. And then you can see that there are more orange boxes. So we have 3 databases, one for messages up there. So each service that needs to store data, it would use its own database. We're done with the one database for the whole thing. I'm going to explain why in a little bit. We still have a message queue. We have a database for users. That's the 3rd box on the right. And then we have another database for revoked tokens. So these are 3 databases. 3 services out of the 5 need to store stuff, and that's how they do it. And then we have this strange blue box, which is new. It's called service registry. That's a very important component of a microservices platform. And I'm going to go into detail on that as well. So this is these are the features. So we have, as I said, 5 microservices. 4 of these are HTTP, Web API, REST, call it whatever you want, but HTTP APIs. And then there's one that's the WebSocket portion. Each service is one Flask app. So we have 5 Flask applications now. They're completely independent. I kept them all in single file. I went back to the simple things in life. So one file for each application. This is it's totally a preference. So if you feel like when I show you these services, if you feel that some of them are a little larger for to keep in a single file, you're more than welcome to split it. However you want. You have models in one file. The same rules that we use for regular Flask apps apply to this, but they apply separately to each service. We have MySQL databases for the two services that store messages and users, completely independent databases. The services run in Docker, so that they're the container images. And then there's the load balancer that's in front of all of this. So all the services are load balanced. You can scale each of these 5 services on their own. So you can have 3 of one, 4 of the other, doesn't matter. And one of the features that, for some reason, I don't know why, but it really, even though I've done it 100 times, it really excites me to do an upgrade without shutting down the service. So nothing goes down when you do an upgrade, which is one of the, to me, one of the most exciting things that you get when you migrate to an architecture of this type. So I'm going to show you, I'm going to do a little demo. I'm praying that the demo gods are good with me. I'm hoping I am not going to have to shut this down for the whole class. So I'm going to show you the final version, and then I'm going to rewind all the way back to the beginning, and then I'm going to do the development in front of you, and the service is not going to go down at all. All is going to be done while the service is online. Fingers crossed. So I need internet too, right? Let's see. So basically, this is the same application. You can chat. So this is on my machine. Unlike last year, where internet was so slow that it was painful, to use. This time I'm hosting it locally, so I'm the only one that can log in right now. So you can type messages. You can do Markdown, and then you can type links, and the links get expanded. So there's a little bit of scraping action there. So that's the application. It's the same application as last year. The client side, the JavaScript side, it's nearly identical. So I have a terminal here. So I'm going to shell into this VM. And am I? Okay, there we go. So the first thing I'm going to show you, there's a bunch of commands. These are the bash commands that I built. So one is mflogs. This shows logging for this. It's a consolidated log stream of all the services. So I'm going to refresh. You can see this is nice, color-coded. Each service logs in a different color. So I'm going to log in, and you start seeing users, tokens, messages. All the services are they log their own thing, and you can watch this stream as a consolidated stream of logs. So these are, as I said, Docker containers. So I can show you that there's a bunch of containers that are running. I'm going to switch here to another view. I have another tab here. Now, this could look scary, but this is a load balancer. This is the load balancer that I'm using. It's an open source project. It's called HA Proxy. You can see it at the top. It's showing me all the things that are being load balanced. And you can see at the very top, HTTP front end. That's the listening portion. So this shows status on HA Proxy listening to requests. So it's not very interesting to us. The remaining 5 sections are the backend. So these are the services that are being load balanced. So the green lines are the instances. So there's right now 1 of each of these 5 services. So I can say mfrun. This is another of these El Cheapo bash scripts. I can say mfrun messages, That's going to run one more of messages. You're going to see it show up in the screen in a minute or less. I'm going to run one more. So you see now there's two. There's going to be a third one. Unfortunately, the way HA proxy refreshes is kind of clunky. That doesn't mean that the load balancer is going down. It's always listening. The refresh, it's sort of, slow. But so we have three. The names, I created the names. It shows the service name, the version. We're running B4 of messages, and then the remaining code is the Docker container ID, in case you want to do something with the Docker API for that container. So I'm going to be a little bit malicious. I'm going to go ahead and I'll take this guy. That's one of the containers, and I'm going to kill it. So this will be the thing crashing, for example. So HA proxy immediately is going to find out that that guy went down. So immediately it's now shifting, traffic to the remaining ones. And in a little bit, it's even going to remove it from the list. Okay, that's one thing. There's another of these MF commands, MF upgrade. So I can do a rolling upgrade. I'm going to wait for that red thing to go away. Should be any time now. And then I'm going to do a rolling upgrade of messages. So we're going to have two, and I'm going to deploy new versions. It's going to still be V4 in this case, but it's going to recycle. It's going to remove these two and then put two new ones. But it's going to do it without ever going down. So, and by the way, I want to remind you, this is Bash. So super high tech, right? It's a Bash script that it's probably a screen or a screen and a half. So super simple. I'm not sure there's going to be a lot of time to show you all these scripts here, but they're there. And if you have any questions and I don't get to cover it in class, you're more than welcome to ask me later. But anyway, here we go. So I'm starting this. So the way this is going to work is it's going to start a new one. You're going to see it there, and then it's going to kill one. And then it's going to start a second one, and then it's going to kill the second one of the old batch. So there's three. Now one is going down. There you go. And now there's going to be one more new one, and then the second one of the old group is going down. So that's how you can do an upgrade without ever going down. So are there any questions about this? So this ends the demo portion, and then I'm going to talk about the theory and how you're probably wondering how the heck did you make this work, and so I'm going to go into that. Yes. I'm sorry, I should have said that. Glad that you asked. So he's asking, how do you connect to the app? So that's so if you look at the Vagrant file, the configuration, it exposes your VM to your laptop on that on that IP address, 192.168.33.10. So you can connect there. If you wanted to see the HA proxy, this other view, that's the same IP address /stats. Sorry, I missed that. Yep. So, well, while we were talking, all this stuff happened, and now we have another two fresh microservices for messages. So when you, let's say if we had a V5 to deploy, you will do it that way, and then you will do the upgrade while the application continues to run. Okay, so I'm not going to spend a lot of time on this, but in case you don't know, I assume most of you know this, but some of the benefits that you get if you go to something like this versus the monolithic approach, like the application that I showed last year. There's less complexity in some parts. This is really, the complexity shifts to a different place. The applications are super simple. You're going to show it, I'm going to show it to you, and you're not going to believe it. Some of these services fit in one screen. They're like the Hello World Flask application, or close. So the complexity is not there. It shifts to the arrows. Remember the little connections that I showed on the diagram? So the complexity shifts to the arrows. And that could be a good thing. What I found that this style of application development works well is if your team has members of different levels of experience, because you can give your the beginner members, you can you can give them a microservice, and that's going to be a very small piece, and because that's isolated from everything else, there are very little chances for that person to make a really big mistake, versus giving them access to a portion of a really big application where all the code is there and they can mess up without knowing it. So I think it encourages a good separation of concerns, and it allows beginners to make a meaningful contribution without risking stuff. So they don't have to to be given simple stuff. They can get interesting work as well. Scaling is pretty obvious. In the monolithic version, we have the flag and the celery, but both were started from the same code base, and they both talk to the same database. So you could scale them separately, but really, if you change one, you're forced to change the other, right? They're basically the same code. With this, we have 5 completely independent applications. At any time, we can scale more or less the different applications. This is more reliable because if one of the services starts malfunctioning, that doesn't mean the whole thing goes down, right? On a really big application, it could be like a portion of the application doesn't work, but doesn't mean that the whole thing goes down. Like it will happen if your flag crashes, right? The monolithic one. The coupling is a very interesting one, and it's very important. I think this architecture encourages uncoupled or decoupled services, which is pretty good. Sometimes if you're working on a really big code base, you don't even realize that you are coupling stuff, and then that makes it difficult to maintain that code in the future. So now you're going to have completely separate pieces of service functionality, and you can basically develop each one as an independent thing. It could be even different teams working on different services. It also encourages clean API design, because the way all these services achieve things together is by using the APIs that each exposes. More choice. This is also super interesting because we are using standard mechanisms for inter-service communication, like for example HTTP. If you find that one of the services is best done in I don't know, in Java, it doesn't matter. You can do it, right? Go, whatever. Python 2, maybe one service needs a dependency that one of the last ones that haven't been ported to Python 3. No problem. Use Python 2 for that one. So this is super great. And then, as I showed, you can deploy and upgrade and never take the thing down. It's always up. But there's no performance here. I'm not gonna. Unfortunately, all this separation and this distribution of work across many services, it has a price, right? If you from the outside send the request, now there's not going to be one entity responding to that request. There's going to be sort of a pinball effect sometimes, depending on what you ask. So, it's slower. So probably most of you have something and you want to migrate that something into microservices. And I have bad news for you. It's very hard. It's super hard. Uh, so I can mention 3 strategies. They're not perfect. They're all a lot of work, unfortunately. Um, so one would be to say, okay, fine. What we've done so far, it stays the way it is. But moving forward, everything, every new piece of functionality, we're going to put it in a microservice. So you basically you start from the present, but you keep that monolith, and you sort of treat it as a grandfathered macro service. You treat it as a microservice, but it's really not, because it has all the problems of a big code base. Another approach is to say, okay, I'm going to start with the monolith, and then over time, I'm going to start taking little pieces and migrate them to microservices. This is probably the most practical approach. And then another one is the line in the sand approach, where you say, okay, I'm going to break this ugly thing into all the microservices, all in one, in one phase. So I'm going to show you how, the tools I'm going to show you, they will allow you to follow either one of these 3 options. Myself, when I did this, I went through this process with this application. I used a combination of the second and the third. I started with the second one, but then I got excited about improving the application, and because of that, I, in the end, decided, okay, I'm going to just redo, break everything at the same time so that I can eliminate some problems that I saw in the previous application. I'm going to tell you about that. Something that a lot of people ignore, I'm going to put an emphasis on this, is that you need that base platform, so the load balancer and the service registry, all that needs to be put in place before you start breaking. If you, I've seen this many times, people think that you just need to run the services. So they start breaking, and then they have 2 or 3 or 5 or 7 or 10 applications. And somehow they manage to make them talk among themselves, and you think you have microservices, but you don't get the coolest benefits, like the easy scaling and the deployment without downtime. You don't get any of that unless you implement the full platform. So it's very important that you do that. I'm going to show you a little bit about that, and then you have to treat that monolith as one special service within that platform to have more chances of success. And another thing that's very important, this was very useful for me when I did the migration, you need unit tests. The work of breaking a chunk of code into a separate service, it's basically a lot of copy-paste. That's what you're going to do that. And it's very easy to make mistakes. So you need to have, before you begin, you need to have a good test suite that exercises the code, and then when you migrate the code to a new service, you also migrate the tests, and that's how you make sure that's the easiest way to make sure that the code still does what it's supposed to do. Lucky for me, I did tests last year, so good. So let's talk a little bit about this platform thing that I'm telling you. The most important component is the load balancer, and some people think that you only need a load balancer when you have load, and that's, at least for microservices, that's not true. The load balancer serves a lot of other purposes as well. So even if you're doing an application that's going to receive very little traffic, it's still a good idea if you want to take advantage of the no downtime deployments or upgrades, or other things like you hear, the coolest companies, they talk about auto-scaling A/B testing, all these, the green, blue, all these things that are typically associated with microservices, they need a load balancer. So you have to have one. There are a lot of options for load balancing. So the 2 open source ones are Nginx, which I'm sure you know, and then HA Proxy. Both are pretty good. In the past, a lot of times I've used Nginx. Today I am not, because it doesn't have a flashy status screen like the one I showed you. HA proxy has that, so that's basically why I went with HA proxy. Nginx is a load balancer plus a bunch of other things. HA proxy is basically a load balancer. That's its main thing. If you're working on a cloud platform, then you can also get a load balancer as a service, right? AWS, OpenStack, all those guys have load balancers. Those are fine too. If you're doing serverless, which this is what I do at work, actually. That's how I am writing today microservices. So I can discuss this in detail if you're interested. It's pretty cool because the load balancing, it's done by the cloud operator, AWS, for example. So you just feed the code and then they do everything else. There's a load balancer, but it's sort of implicit. They do it for you. This is, for those that are not familiar, the Lambda and API gateway services in AWS are the best example. And this is probably the only one that support Python. I'm not sure if the other serverless options do. I don't think they do. And then finally, if you need to go nuts on load balancing, there's the hardware option. You can buy a box that load balances, and at least at work at Rackspace, the F5s are the ones that they always sound to be very reliable. So okay, next service registry. So you saw that in the diagram, the load balancer was connected to the service registry. So the whole point of this is that you have sort of a cloud of little services, right? You have a bunch of things running, and somehow you need to keep track of what's running because the load balancer needs to send traffic to those things. So the way you do that without going crazy is by having sort of a database where you list all the services that are running. And then the load balancer looks at that database, and if it notices any change, like when you saw me start a service and then immediately after the load balancer reconfigured itself. So the load balancer looks at the service registry and updates its configuration when something changes, either a new service showing up or a service going away, either one. So that's how you get all this automatic, I start a service and it's immediately connected. As far as options, there's a bunch of options. They're all open source. So etcd is one that this is the one that I'm actually using today. But there's a bunch of others, and they're all pretty good. There's even one from Netflix that's been it got some publicity not too long ago. So anyway, you can check them out. They're probably all on GitHub. Most of them are anyway. So another component that's important is logging. When you have a monolith, you just log and you get a log file, and that's usually enough. But now we're going to have a lot of services. They're all logging. So it can be kind of messy, especially if you need to debug something. If you have, in this case, 5, but maybe if I'm running 3 instances of each service, then I have 15, right? 15 log files. So you need to find a way to consolidate all that into a single stream. And there are a couple of open source options. The one that I showed you today with the color coding, it's a log spout. It's specifically for Docker. I wanted to keep the VM small to increase the chances of all of you being able to run it on your laptops, right? If size of VM was not a limit, I would have installed the ELK stack, which is the Elasticsearch, Logstash, and Kibana. So that's the leading open source solution for logs. But then there are many commercial ones as well. I list a few here, but there are more. So plenty of options. Ideally, you should decide on one if you're going to do this. And then I said that I'm using Docker containers. So the idea with the containers is that there might be varying list of dependencies for each service, and running everything as regular processes in a host complicates things if you have conflicting dependencies, for example. So that's one reason why using a container, which I honestly I see it as kind of a process, but then from inside the process thinks it's running in its own machine. It's all for itself. But I mean, it's really a process, so it's not such a big difference. One very important thing that you get by using containers is that, as you're going to see later, all my Flask apps, these 5 services, they're all running on port 5000 on the same machine. And Docker takes care, each container has a virtualized port 5000. Ends up being some other port, I don't really care which one, but Docker does all the management for me. If I were to do this without Docker, then I will have to, each time I want to run a service, I need to decide which port to put it. So I don't have to worry about that, because I let Docker find a port, and then I use the Docker API to get the port number. So normally, I'd like to see a container as a single process. Sometimes in practice, you find that you want to run other processes, so more than one process in a single container, and that's fine, and I do here. But typically, you have to think about containers as one main process. In this case, it will be the Flask application will be the main process. And if you need some auxiliary thing, maybe a cron job, that's something that's totally fine. And as I said, Docker is optional, but it saves a lot of trouble, when you're going to have a lot of services. Application state. This is a big topic. So there are basically 2 kinds of services in terms of storage. There are services that hold state and services that don't. So stateful or stateless. When you have a stateful service, if you kill it, you lose the state. And that's basically, you have to figure out a way to save that information somewhere. So an example would be, for example, MySQL process, right? Now, if you have a stateless service, if you kill it and start another one, it doesn't matter, because it's only code. So what we want is we want to use the stateful the stateful services outside of our application as much as possible. So we're going to have a database service. We're going to have a message queue service. These are stateful. We're going to make sure that those never go down. So there are options to scale and to make them highly available. You're going to use those to make sure that those are super reliable. And service registry, that's another one. That's another one that's stateful. But then when you develop your application, as much as possible, you have to make your own services stateless, relying on the stateful-based services for any storage needs. That means, I showed you before, that the messages service, for example, I can kill and start new ones, and nobody cares, right? Because the data is not there. It's just the code. So if I need to scale it up, I just run more. If I need to scale it down, I start killing services, and nothing is lost. So ideally, your application should be built that way. So I'm going to give you a specific example. Last year, I used a SQLite database. This is a file on disk. That's a big no-no for this. You cannot have a file on disk be your database, living in the file space of your service. Because if you kill that service, you're killing the database as well. So today, I'm using MySQL databases. There's a MySQL service for this. So important stuff. For development, you can use SQLite if you want. But on production, you can't. Or I guess you can, but it makes everything way more complicated, so you don't want to. So last year, we had a single database, and all the different parts of the monolithic application just went to that database. If we need to migrate the database, then the application will have to basically be updated as well. There's no way to migrate the database while keeping the application running. So that's a problem. So what we are going to do now is, there's going to be some rules. I'm going to talk about that later. But in addition to that, each service that needs storage is going to use its own database. So if you change the user's database, we don't want the messages service to be affected. So the messages service cannot even see that database. If it needs anything doing with the users, it needs to send a request to the user service. So the user service owns the users, the messages service owns the messages. Does that make sense? This has a really bad side effect. Remember joins in relational database? Say bye-bye. It's very difficult, right? If you need to join, let's say in this case, messages and users, you have to do it in the application because the databases are separate. And that's one of the prices that you need to pay, and you need to consider that, right? Maybe that's a deal killer, and then microservices is not a good idea for some type of application. Another thing that's important, I blogged about this, by the way, so if you want more details, you can find an article on retries on my blog. So ideally, we want everything to be up all the time, but ideally, right? Things happen usually. So there might be brief interruptions in service. So you want to make sure that when you send a request, like a service sending a request to another service, it retries it. Because if you just happen to catch it in a bad moment, you want to try a second later, and probably you be successful if the first attempt fails. So it's a good idea to basically retry all your requests and ideally encapsulate the retries so that you don't have to, at the application level, think about retries. And I'm going to show you that too. A pretty good idea, a pretty good algorithm to do retries that you may have heard, it's called exponential backoff. The idea is that if you send a request and it fails, you can try it right away, a retry. If it fails again, to do the third retry, you're going to wait a little bit more. And the fourth, you're going to wait even more. And basically, you keep spacing them out, until at some point you're going to give up. But the idea is that you have to give time to the service to recover if it's sick. And if you don't do this, then imagine the services goes down, and then all the other services start flooding the service with requests and retrying, and they keep sending requests non-stop. And then by the time the service wakes up, it has a backlog that's impossible to service. So the idea is that not flood a service that's down with lots of requests, just give it space to recover. Okay, another bad news. So imagine you have, like in the example, there are 3 messages services running, right? You have 3, and the load balancer is splitting the traffic among those 3. And now you need to upgrade it. So let's say we were at V4. Let's say we want to go to V5. And so there's going to be a amount of time where you're going to have V5 and V4 services running at the same time, receiving both traffic, right? Because we don't want to stop, right? We want to do this while running. So initially, you're going to have 1 V5 and 3 V4s, and then we're going to kill 1 V4 and add another V5 and so on, right? So for an amount of time that's not minimal, right? It could be a few seconds to minutes, depending. You're going to have both versions running. Both versions are going to be using the same database. So if you migrate the database in a way that V4 will crash, that's a problem. So you're going to have to think about, there's going to be rules about how and when you can make changes that are breaking. If it's important for you to then upgrade the service without putting it down, right? Because without stopping it. So when you do a migration, you're gonna have to think very carefully about this. And I'm gonna give you one example just so that you realize how difficult this is. Imagine you need to add a column to the database, and you want that column to be non-nullable, so it cannot be null. So you create a migration and you add that thing to the database for V5. right? And V5 knows, it always sets a value for that new column. But V4 is still running, right? And V4 knows nothing about that column. So if you need to insert a record in that same table, it's not going to know. It's not going to set a value for this column that cannot be null. So V4 is not going to, and it's going to crash. So you can't do that, basically. If you need to add a new column, first you need to add it as a nullable column to be minded of, the old version that might still use it. And then after you migrate everything, so you're running all on V5, then you can add another migration that changes it to non-nullable. Does that make sense? It sucks. Honestly, it's very difficult. And you should test all your upgrades on a staging server before you go to production, just because of that, right? Because it's difficult to think in those terms. So likewise, API changes, same thing. Each service will expose a public API, right, that the clients will use and the services will use among themselves. You cannot change that in a way that's breaking for all their clients, right? If V4 and V5 of messages expose a different API, how other services know, how to talk to the service? So you have to think very well when you define your API. I think this is a good thing. It basically enforces, the good thinking about APIs. You need to make sure that the API is good and that you like it, because it's going to stick with you for a long time. It's difficult to change them. Sometimes you are going to find that a feature requires changes in multiple services. But basically, you have to coordinate, service changes among a few services. I'm going to show you an example later. So it's very difficult to upgrade those services. You need to basically orchestrate the upgrades so that you never break. You're going to be upgrading each service independently, even though they all together implement this new feature. So you need to make sure that you remain compatible with the pre-feature state of your application as you make the upgrades for each service. This is also very difficult. I think it also encourages it encourages the idea of deploying applications one bit at a time. So basically, if you're working on one service for this big feature that spans multiple ones, when you're done, you tested it, you throw it over the fence and deploy it, and then you keep working on the remaining ones. It's good for that. It basically promotes this decoupled architecture. That's very good for maintenance, over time. So this is how I demoed this. This is the life cycle of a service. When you started, in this example, it will be this mfrun tool that I showed you, which basically starts a new container, a Docker container. The service, as part of its starting up, it'll say, hey, service register, service registry, I'm here, I'm running. So that's going to update the service registry. On the other side, the load balancer is watching and say, oh, something changed here. I'm going to reconfigure myself. So it generates a new configuration and then it applies it. And now the service is online. So the load balancer is going to start sending traffic to that new service, but it's going to continue sending traffic to all the other ones of that same kind. It's going to split the traffic, right, among all of them. Now, depending on the platform, the service may send keep alive signals, say, hey, I'm still here, I'm good, I'm running. Or in other platforms, there's some component that checks that the service is running by sending a test request, a health check. Either way, the whole point is that if the service dies, then you want that registration in the service registry to be removed. And when it's removed, the load balancer will pick it up. That's the yellow and red that you saw. The load balancer detects that immediately and then updates. But basically, that's how this works. Are there any questions? I believe I have one more slide for this section. Any questions about how the microservices start and end? The life cycle. Yes. Okay, so you mean auto-scaling. So there are many ways to implement that. So if you're working with a homegrown solution like the one I have here, you can use any metric. So, but by the way, I did not implement auto-scaling. The scaling is in this example is manual, and I showed you you just run more. But if you wanted to do auto-scaling, you can have an endpoint in each service that reports statistics, how many requests per second it's handling, for example. And then after some threshold, you say, okay, this service is doing too much work. I'm going to start a new one. Kubernetes does that, for example. AWS does it too. Yeah, pretty much any professional level. They're very complex, unfortunately, but they all do. Yes. Very good question. So service registry, I'm using this etcd service, but all the ones that I showed and any other, it's assumed that they are highly available. That means you can run more than one instance of them. And these are stateful services, so it's a very difficult problem to basically have a distributed service like these that are running, and if a node comes down or if the network has trouble, they keep going. They're pretty good at that. So for this example, in this VM, I'm running one instance, but you can run 2, 3, or 10 of the service registry. And that basically that addresses that problem. You want to make sure that you have a backup. So any node that goes down, you have a few more. Load balancer, unfortunately, you keep going up. You can deploy multiple load balancers, but you need a guy on top that load balances the load balancer, right? At some point, you have to stop, right? In my experience, what I do is I deploy more than one load balancer. So you have multiple addresses. It could be different regions if you need to make sure that different data centers, for example, or regions if you're in a cloud environment. And then if one goes down, you can use the other one. Eventually, at some point, you always want to have one, and there are many solutions. You can play with DNS as well, but then the DNS is you have one, right? So what if that goes down? So yeah, it's a difficult problem. You should be prepared to have multiple connection endpoints. So this is only a recommendation. I don't know if you guys heard of the 12-factor app. This is a so it's 12factor.net. It's a website that lists these 12 that they call them factors. So a lot of the ideas behind microservices agree with this, even though this is not specific to microservices. Basically, it's the way to build modern distributed systems, and it has a number of very good points, which we are adhering to when you do microservices. So I recommend that you. This is a short read, so just take a look at this and start thinking in these terms. Okay, I'm behind, by the way, so great. So for this application, as I said, to implement the services, these are regular, old school, the thing that we know and love, Flask, right? So there's no change there. For the platform, I use HAProxy for load balancer, etcd for the service registry. etcd is not a service registry service. It's a general purpose, very quick storage for anything. But basically, the etcd people may hate me for this. I'll make an analogy it doesn't look like there are many Windows guys here, but do you guys remember the registry in Windows, this hierarchical structure? Okay, that etcd is that on the web. So basically, it's a tree structure. Okay, you don't like it. It's a tree structure. You use HTTP requests to set or get the values. So it's highly available and it's very quick to access. It caches stuff in memory, it's super fast. So that's basically the idea. And if you have multiple instances, when you change, you send a request to one, it replicates on all the others. So it's a little bit more complex than the Windows registry, but the whole idea, it's kind of the same. It's a configuration place. So we're going to use it to store our services there. Now, remember that HA proxy, the text changes in service registry, but HA proxy knows nothing about etcd or anything. It's a load balancer. So the piece that makes HA proxy update itself, it's called confd. This is an open source tool as well. Confd sits in between a load balancer, any load balancer, and any service registry. It supports a bunch of them. And you give it a configuration template for your load balancer, and then you tell it where, in that tree structure of etcd you store your services. And then confd watches the service registry, and if it changes, it runs the template again with the new data, and then it tells HA proxy to restart. That's the magic. We're going to use Docker, just plain Docker for our containers. Logspout is the logging, which is actually really nice. MySQL for databases, because SQLite is a no-no for this type of thing. And we are still going to use Redis for the WebSocket part to do so that any service that needs to push something to the client via WebSocket can do it by pushing on the message queue. Lucky for me, there are a bunch of things that are already available in the Docker universe, so I didn't need to build a lot of, all this base, the base platform. I had to build only a couple things, but most of them are already existing. And that applies to Logspout, which exists. I'm using it as is. MySQL, there's a container for MySQL, and Redis as well. etcd has a container that's an official container. My opinion is that it's kind of difficult to start, especially if you need to set up a cluster, which you will for production. So I basically wrapped the original container into this easy etcd, which is a container that I created, a container image. That makes it a little bit easier. But you don't have to use mine. And then I did the same for HA proxy plus confd. I created a container image that has all of that configured. You don't have to, last year I showed, or I included in the repository for last year a configuration example for Nginx, right? And then if you wanted to implement that, you need to take that file and then look at it and edit it according to your needs, whatever. So now all you need to do is take this container and start writing to etcd at the proper place, and this container knows how to generate the configuration. So super simple. These two, you can find them on mine. Well, actually, all of them are on Docker Hub. Mine are also on GitHub if you want to see how I've done them, how I implemented them. They're simple. So I started thinking about how to do this, and I knew I needed a bunch of scripts. So all this bash, scripting that would allow me to implement this platform. So Microfrac admin is the repository with all these scripts. And there's a bunch of them. I'm going to show many of them today. If I forget, I apologize, but then ask me about it. If you look at the second line, shows the scripts that make the deployment to Vagrant. If for any reason you cannot deploy to your laptop in a VM, and you want to do it on a cloud server, something else, something that's not a VM in your laptop, those scripts should work as well. You can look at the Vagrant file to see how I run the commands that provision this empty Ubuntu VM, make it to install this application. So I'm going to show this later. I also was thinking that there's a bunch of things that all the services will need, right? So for example, we want all these services to talk to the service registry. That's going to be a common functionality. The unit tests, there's going to be, you probably seen me, I usually, when I unit test an API written in Flask, I take the Flask test client and then add something on top, because the test client, as you know, it's not really made for APIs. It doesn't assume, the defaults are not proper for APIs, right? It doesn't start with JSON as a content type, all those things. So I usually subclass the test client, and then I implement the defaults for API testing, so that I don't have to write so much test code. So all that could be, it's going to be common for all the services. When services need to talk to each other, they're also going to be, you're going to have to send a request, and you want retries to be implemented, as I said before. So all that functionality is common as well. And finally, authentication, same thing, right? You're going to be sending a token to any of the services, and they need to verify the token, so that's common functionality. So what I've seen different approaches that people follow to do this. They always dance around the best approach. Very few people implement the best approach. So people, for example, they put all the code, all the common code in a service, in the first service, and then when they need to do the second service, they copy the files, and now you have a copy, right? But then on the second service, you find that there are some things that you can improve. So you change those files, the common behaviors, in the second service, but never go back to update the first, right? So now you have differences. And then you go to the third service, and you end up with a lot of differences on the common functionality among services. So that's kind of a bad idea. It would be a good idea to create a package, a Python package that has all that functionality. And then basically you treat it as another dependency, like if it was a package you get from the cheese shop, from PyPy. So if you're doing open source, then just create the package, put it on the cheese shop, and off you go, right? Pip install, you're good. But probably many of you, that code is going to be proprietary, right? So you can't go on PyPy. So the solution, which a lot of people think is difficult, is surprisingly easy. You can modify pip, configure pip, to install packages from a directory in your machine, or whatever, network server, whatever. So I decided to take that approach to show you how that is done. So the option, if you do it with pip, it's find links. So you can say pip -- find links, and then a directory. And then when you install a package, if it's in a directory, the directory that you put after find links, then it'll install it from there. So that's what I did. So I can show you if you want. Let's see. So microflag common is the second repository that I'm showing you here. And this guy, I'm going to show you the first version. So I'm treating it as if it was a package built by someone else. So its version, it gets its own versions. Each microservice will use, the proper version. There are 3 right now, and if you go look, the services use different versions, because I don't think I need to upgrade all of them when I make a new release. But as you need to do the upgrades, you do it. And there's a make wheel script here that bash again. Basically, it creates wheel packages for all the versions. So if you say mk wheel all, it'll just find all the released versions by looking at git tags, and it build a package for each one of them. I'm going to show you that later, how that works. And then in your requirements file, you just include this thing. In this case, it's called microflag common, and you specify which version you want. Another thing that I was thinking when I was preparing to do this is that the way I implemented tokens for the monolith was kind of inconvenient. I'm going to remind you how that works. Basically, when the user requested the token, the server will just create a random string, store it in the user database as a token, just So it's just a random sequence of characters, and then pass it on to the client. And then when the client sends it, it will look it up in the database. So now users is in its own service, and the tokens are going to go to any of the other services, right? So these services get a token and have no easy way to verify it. How do I know if the token is valid? They need to send a request to some other service. It could be users, or it could be tokens. I'm going to talk about that, but it's basically it adds a lot of complication. So I was thinking that this would be a good opportunity to use JSON Web Tokens. So I don't know if you heard, but JWT is a standard. So you can create a token that has a signature. And you can verify the token just by checking the signature. You don't need to ask somebody else to verify the token. So each service will be able to check a token and make sure it's valid without sending a request to some other service. So I decided that at some point I wanted to switch to JWTs. Yeah, I added a note here. Some people don't like JWTs. I don't know if you heard, but every once in a while someone comes saying that they're awful, they're insecure, they're very exploitable. So what you need to do to make sure that you are protected, I'm gonna bet if you're using JWTs in this room, there's gonna be at least one, probably more people that don't do this, and then you are definitely vulnerable. When you check a JWT, you need to check the signing algorithm. Make sure it is the correct algorithm, the algorithm that you use to sign the tokens. And all libraries allow you to do that, but they don't do it by default. So I was thinking about how to split this application into services, separate services. And basically what I decided to do is look at the URLs. And we have a bunch of URLs that return the static content, the JavaScript and CSS and HTML. So basically the UI. A bunch of things for users, so /API/users/ blah, blah, blah. There was one for tokens, to get a token. The messages ones and the WebSocket one, socket.io. So I said, okay, fine. I'm gonna use these as a guide on creating microservices. So each group of URLs, they're gonna go on their own service, and that's how I ended up with 5. So, okay, it's not too bad. There's hope. So okay, so that's the first part. Maybe I should stop there. And any questions? Because the rest is me showing you how I develop this. So it's going to be you're going to be watching me do stuff, and you can do it if you have the thing running right now. You can do it along with me. So any questions? Yes.
For the JWT signature validation,
Yep.
you have to have a secret key to validate that signature.
That is correct. So there are a couple ways, but yes, when you generate signature, by the way, I should mention this. The user session in Flask, it's very similar. It's not JWT, but it uses the same concepts. It's very similar to JWTs. So you need a secret key, like with the Flask user session. So all the services need to know that key. That's one option. Another option is you can use public key cryptography, where you have public and private keys. That will be if you want to make sure that the secrets are not distributed among all the services. So you can go with that with JWTs as well. But yes, that is true. The secret key needs to be known by any service that verifies that needs to verify the signature. And like the user sessions, the contents are not encrypted in a JWT, so make sure you don't store a secret there. There's an extension or a separate spec for encrypted JWTs. Yeah, so you can do that instead if you need to store secrets inside the token. But yeah, JWTs are nice because you verify the signature and then you have the user ID. It's in the token, so you verify the signature. If the signature is good, you can get the ID, and now you know the user without talking to anyone. Any other questions? Okay. So I needed to do this. You have to start from somewhere, right? It's very difficult. You have the thing running as a single application, and my decision was to use the easiest service, and the easiest service in this application is the UI. Now, you may think the UI is not a service. What are you talking about, right? Uh, that is true in a way, but it's serving static files. So it is sort of a service. Now, in a real project, you will probably be crazy if you implement the UI serving in Python, right? Probably all of you, they have Node people doing this, right? And that's totally fine because, as I said before, there's choice, right? It's a microservice. It's talking over HTTP, so you can do it however you want. Now, I use Python because this served the purpose of allowing me to create this base platform. Where I was creating the UI service. At the same time, I polished the load balancer and service registry, all that interaction, and I didn't need to worry about authentication tokens, databases. The UI is just static files. So I got like 90% of the base platform going by testing with this service. So this is a summary of the endpoints that serve the user interface. So it's basically slash gets the HTML and then slash static slash whatever. It serves all the client code. So this is the third repository out of 7. So microflag UI. It's also on my GitHub. If you have the VM up, there's a directory for all the the seven repositories are at the top. So you log into your so you do Vagrant SSH, and you have directories for all of these. So you can look at it there. So it's actually super simple. The application has an app.py. So for all the services, I use app.py for the actual Flask code. Some people don't like that. They get confused because app.py has an app object inside, so you need from app import app. They get all confused. They think it's the same thing. They don't see the difference. So if you are in that camp, that's totally fine. Just use something else. One big reason why I decided to go with app.py in all the services is this somehow irritating thing with the newest Flask versions that you need to put in an environment variable the name of your app, right? So I wanted to have to set it and forget it. So Flask app is set to app.py, and then I can say Flask run and never think about it. In all the services, it's the same. So that's one big reason why I decided to not call it UI.py. Then I needed to change the the configuration, the environment variable, depending on which service I'm working on. But as I said, I don't want to be a model. I don't think you should do this if you don't like it. So there's an app.py, config.py, and then the files, the templates and the static. So pretty standard Flask app and a requirements file. So I'm going to show you this beauty, which is super simple. Wow. Okay. There you go. So I'm going to go to the first release. And so this is the whole thing. So application is that. So basically, it's a Flask application. I'm using like last year. I'm using Flask Bootstrap for generating the the HTML that includes the Bootstrap libraries, all of that, and basically I render the index HTML as a template. It doesn't need to be a template, but I have some URL4s in it, so I kept it as a template. This imports the configuration based on dev, prod, the usual stuff. You probably see me do that many times before. this line here. And this is not necessary, right? We don't need this anymore. With current Flask versions, you don't need this, but I miss it. So I really like this. I think this was better. So now I kept it there, but I don't really use it. It's just, I should have removed it, but I forgot. But yeah, you don't need that. So super simple. This is a microservice. So that's it. Probably not very interesting, but if you want to see the config, it's also super usual stuff. I create a class for each. So there's a base config and then subclasses for development, testing, and production. And for this one, there's no behavior, right? So there's nothing to set. But the great thing is that this is so simple that it allowed me to create, the basis for the following services, which are a little bit more complicated. I'm going to show you the requirements. I have that's the common package, right? So that's not on PyPy, but the way we're doing this, it gets installed as if it came from the cheese shop, though it's in a directory locally. The service supports a .env file. If you have a .env file with variables, those are imported into the environment. So one of the things in the 12-factor app, this list of 12 things, one is that you should configure everything through environment variables. So that's a pretty big topic. So anything you want to set, you can put it in a .env file. This file is not going to be on source control. You're going to set it specifically for each instance. The reason it's not in source control is that it may contain passwords, secret keys, all those things. There's unit tests. So I have a test.py. Probably not very interesting, but let's see. So test.py. For this one, I created just a simple test just to make sure that I can get all the framework going, but there's really nothing to test. So this one, it imports the test case not from unit test, but from the common library. I have a subclass that has all the extra stuff that I need to test without having to think about setting content types, the JSON settings, all that stuff. And I can do self-get here, and that basically goes, it sends a GET request through the Flask test client. And this returns the response, the status code, and the headers, so as a triple. And then I became quite a fan of talks for driving the tests. So I implemented talks config file that runs the tests. The tests include coverage. So I get a measure of how effective, how much of the code the tests are testing. And also runs a second task with Flake 8 to make sure that the code is clean, in PEP 8 terms. And to make sure that I can, since I'm installing here packages, I need to set the directory where I have these common packages. So that needs to be set in the environment. Okay, what else? Dockerfile. And then, so if I needed to test that service, I can run it on my laptop, isolate it from everything else, and just test it, right? I can go to localhost 5000 and run the thing, make sure it works. Run the tests, all that. So then I built a container image out of this. So for this, I use Python 3.6 because why not, right? And I'm using this Alpine edition. Alpine is a Linux, a tiny Linux distribution that's fairly popular for Docker images, just because it's small, way smaller than say Ubuntu. So I use that one. So that there's a Python 3.6 official container built on top of this Alpine Linux. So I use that, and basically, if you're not familiar with a Docker image, it's basically sort of a script that installs everything. So you can, oops, sorry. You can see the commands. There's a pip install. It installs gunicorn as well. And then expose 5000 that you're declaring the port that this runs on. And then at the end, you give it a command. And this is a command that's going to run when you run the container. So everything else above the CMD line, that executes when you build the container image. So it creates that image in some place in your disk, and then compiles all that into a single file, an image. And then when you run it, it's going to run the command that you declare as the command that starts the container. And as you can guess, that's also simple. So boot.sh. At the bottom, you can see we're running gunicorn. So the service starts the usual way. I'm sending all the logs to the hyphen makes it go to standard out and standard error. That's important because Docker finds those logs, and anything you print, it goes to the Docker logs. And then there's this thing here where this is the magic that makes the service show up on the service registry. There's a module in the common package that basically writes itself to the service registry, and I'm running that before I run the service, so that it's up by the time gunicorn starts, and then HA proxy, the load balancer, will find it. One nice feature of the service registry, I can show you that if you want, but so one of the modalities in which you can write to the service registry is to write with an expiration. That's what I'm using here. You can say, I'm going to write this with a timeout of 50 seconds, I think I'm using here. So you write it with a timeout. By that time, when 50 seconds pass, then it gets removed. The service removes it from you. You don't have to do it. So the idea is that this thing will continue to refresh that registration. So it writes it with a timeout of 50 seconds, but then 15 seconds later, it'll refresh it and push the 50-second limit forward. And it keeps doing that. And the idea is that if it crashes, then it's going to stop doing it. In 50 seconds, the thing's going to go away, and that's how HA proxy then removes it from its configuration. So that is how the register works. That's in the common package. There's a module that does all that in a container. So this is a lot of functions that deal with Docker, that determine if the service is running under Docker. And here at the bottom is the register function. And this function has a loop which it continuously refreshes the registration. So when this container dies, this is going to stop, and that's eventually will remove the registration and update the load balancer. Are there any questions about that? Does it make sense? It's pretty reasonable. So that's a microservice. I think this is probably the worst. It's downhill from now on. So those of you that are running this right now, if you want, you can do it. I'm going to cause some trouble here. So this thing is running the latest, the end of the class project. So I'm going to reset it. So I'm going to say mfkill all inside the VM. So you need to get in SSH into the VM. You can say mfkill all. If you're doing it, make sure you watch the load balancer, because this is pretty cool. yellow, red, it's all going down, right? I'm removing all the services. The load balancer. Let's see. That better? Yeah, no problem. Okay, so now you know there's no micro flag anymore. If you connect, this is a load balancer that it's up, but it's not load balancing anything, right? So I'm going to go to the UI service. I'm going to reset history to version 1. There are 2 versions of this, so I'm going to go to version 1, get checkout 1. That's the label. There's a build bash script that basically generates, it runs this Docker file that I showed you and generates the image. So this is going to pip install all the requirements, all of that. The common package is already built, so it'll find it. It was built when this Vagrant VM was first deployed. I'm going to show you later how to do it from scratch. So I'm going to show you how to build those wheels later. So almost there. Okay. So now I can say mf run. You've seen that before, and run the UI. So this you saw in the boot.sh. There's a call to the register function, and that translates into something written to the etcd service registry. Confd running inside the container that runs HAProxy will say, oh, something changed. I'm going to regenerate the HAProxy config, and then I'm going to restart HAProxy, and that ends up, exposing the service. So now I can go back to this tab. So I'm going to refresh this, and now we get, this is serving directly from the UI service. Now, of course, if you look at the console, you're going to see errors because this is trying to talk to the API, and we have nothing yet, right? That's expected, but at least we get the UI. So, oops. I think I covered everything here. Yes. Now, so remember, I told you that there are 3 approaches to working with microservices, or to migrate. So imagine you have the Flask, the old Flask, right? The one that runs in a single process plus Celery. So let's say you have that running in your laptop, and now we took the UI, we broke the UI service out of it, and now we have it as a separate service. So what we can do now is we can write entries in the service registry that point all those /API /blah blah blah endpoints back into the old flag, the monolithic one. So the service that serves the UI is going to be the new microservice. But for everything else, anything that starts with /API URLs, we can basically configure the load balancer to send it to the monolith. Does that make sense? So this is exactly how you will do out of the 3 approaches, the middle one, where you start breaking pieces out into services. So each time you break a new piece, you remove that from going into the monolith by changing etcd. Does that make sense? So I think I can show you that. I don't have the old flag running, but oops. So one of the tools, one of the scripts, it's etcd dump. This shows the contents of the service registry. So this is a hierarchy, as I told you. regulated all the all the time. It's like that. So you have a services at the top. So then under services you have the service name. So there's only one right now, UI. And under that there are two keys. Location, that gives the URL that you're going to use for that service. In this case, it's slash. We're going to use this is going to be the catch-all. Anything that doesn't fit any of the others that we're going to add later is going to go to this one. And then there's an upstream section that lists all the instances of your service. And right now there's only one. And for each service you have a name. That's the name that shows up in the load balancer. And then as a value you have the URL, which I get from the Docker API in that container.py module from the common package. So I think so this is unprofessional. I'm going to stop the slides so that I can copy paste this. So if you wanted to expose the monolith, I'm going to use curl to write new keys into etcd. So this is location for a service that's called Monolith. And then the other one is the actual location. And so this is, I'm using 10.0.2.2. This is specific to Vagrant. When you create a Vagrant VM, from inside the VM, 10.0.2.2 is the IP address of your host. So your laptop will be 10.0.2.2 from inside. So I'm saying port 5000 on 10.0.2.2. So if I run the old Flask in my laptop, then this will see it. So now I think this is going to show up, and this is basically how you do it. So let's see. Let's look at etcd again here. So now we have UI and Monolith. And Monolith is /API, so that's the prefix. So anything that starts with that will go to 10.0.2.2 port 5000. So I called it server. I could have called it server 1 and then add more. If I wanted to scale, this application remains scalable as it was, originally. You can put more. Does that make sense? So do you realize it's showing red because I'm not running it? So the moment I run it, it'll turn green. And HAProxy is pretty good. It's constantly testing, right? So if anything goes red for a moment, the moment you start it, it'll go green, and it start sending traffic to it. So okay, I'm going to reset this. So now I'm going to delete that and go back to normal. So I'm sending a delete request to delete that branch, the monolith branch. That went away now. So we're back having only UI, and that's going to update in a minute. So at this point, I said, well, should I continue like this, breaking little things and keep everything running? There was the problem with the tokens. As I mentioned before, the way the original Flask uses tokens is very inefficient for a microservice architecture because it requires a request to verify the token. And I said, nah, I'm going to just break everything. So at this point, up to this point, I was planning to do a gradual migration. At this point, I said, well, I'm going to use the opportunity to improve the design of this app. So at this point, I said, okay, from now on, I'm going to break the remaining services. And basically, from now on, we're going to have a partial service until we get all the services deployed. But at least I hope you can see how, if you decide to go with a more conservative approach like this, then you will continue like this. And you will keep all your technical debt will still be there, right? You will keep it. You will be forced to keep it because you have parts of the application still running, the old stuff. Okay, let's go back to full screen. So 3 more minutes until the break. It's probably a good time to break then. And then we're going to look at users, how to deploy users, the next service. Sounds good? Any questions? Let's use these 3 minutes for any questions you have, if you have them. Yes? How do you handle SSL? Good. There are many options. I did not implement SSL for this particular installation. This is supposed to be, for testing. Typically, what I do is I make the load balancer terminate SSL. That's the easiest. Putting SSL all the way to Flask is kind of painful. So, all the services expose their endpoints in the same host and the same. Basically, it's /API/ something else. So, from the outside, it's all the same host. So you can use a single certificate for all of them. If your services have different host names, then that's a problem. Then you need different certificates. Then you will have to send the SSL all the way to the services. In that case, you will not use HA proxy to terminate the SSL. So typically, that's really uncommon. Typically, the load balancer is in a safe area, so the communication between the load balancer and your services, typically you don't need SSL. If you do, then you can re-encrypt from get the load balancer to decrypt, so be a point where SSL is terminated, and then start a new SSL session into the services, and then handle the SSL in the services. If you want, like Gunicorn could do that, for example. But you might as well just send the SSL all the way. So HA proxy will, well, actually, I'm sorry, no. In this case, it needs to look at the URLs. So you will have to do that, actually. So SSL will terminate. So you can configure HA proxy or Nginx to terminate SSL, and then you will do another SSL connection into the services if you have to. Typically, you don't. And the standard is that now you are in a secure part, so you can go without encryption. Does that make sense? Does that answer your question? Yes. Mm-hmm. Well, I just realized when talking to him that you cannot pass through the SSL because the load balancer needs to look at the URLs to know where to forward requests, right? So you have to terminate SSL. The question is, do you want to establish a new encrypted connection, in between the load balancer and the service? And you can if you have to. If you need to do that, you can. Does that make sense? And then Gunicorn we configure with the certificate, all that stuff. Any other questions? Okay, so let's break. I'm not sure how long. Do you know how long the break is? 20 minutes. So let's meet 3:20 then. And if you want to talk about any Vagrant problems, all that stuff, I'm here. I'm available. Okay, should we continue? I think most of you are back, right? Are you good? Okay. Okay. So we have our first service up, right? So next step was to pick a second one. And for the second service to implement, I decided to go with one of the ugliest ones, the ones that have database. So I decided to go with users. So users will have its own database. This is the summary. The black endpoints are the ones that existed in the original application. So you could get a list of users, and that was open to anyone. So you could get the list of connected users without logging in. So you will see the bar on the right. It'll show who's chatting before you log in. So that didn't take off. And then you could send a token to get the list if you have a token. So after you log in, then you do send the token, and the token in that case is used to mark your user as active. So if it's online, then it'll show up on that bar on the right. You could log in by sending a post request that will create the new user. And you could modify the user, like rename it by sending a token, that required a token. So all these are either token optional token, but because I decided to put the token service separately, right? I initially decided to divide by family of URLs, right? Consider the problem where the UI needs to register a new user and get a token. So you send a request to the user service, and basically that registers the new user. And then you send a request to the token service to get the token, and the token service will receive a username and password and needs to validate that before giving out a token. But the token service doesn't have access to the user database, right? So probably, a decent design will be to have users and tokens in the same service. I decided to do it this way because I think it's a good example of two services working together to get something done. Okay. So the way this is going to work is the token service will get a token request with username and password, and it'll have to ask the user's service to verify those credentials before it gives out the token. So the way that's going to happen is in the user service, we're going to have a new endpoint that's specifically made for that. Any other service that needs to verify credentials will use the red one. So it'll be /API/users/me. Basically, it returns information about a user. It takes basic auth, so username and password. And if those are valid, then the user service will return the user information. If those are invalid, it'll say for one. Okay, so that's the token service, which we haven't deployed yet, will use this. But I was thinking ahead and decided to add this new endpoint. So as far as structure, it's very much like the UI service that I showed you before the break, except that this one's longer because it's got database models, right? So we're using Flask, SQL Alchemy, the usual stuff, the same thing that I always do. For the endpoints that take tokens, it's going to import the token validation from the common package. And then just to show you how this will work if you have database migrations. I added Flask Migrate, which I didn't use last year on the monolithic version of this app. This time I decided to put it there just so that you realize that you're going to have migrations for users and you're going to have migrations for messages later on when we add that service. And they're going to have completely separate histories, right? They will upgrade on their own timelines independently of each other. This mfrun script that I showed you that bootstraps a new instance of a service, that script, which is in Bash again, it knows services that need a database. There's environment variables that declare or define which services need databases. So if you're starting a service that needs a database, it'll go look and talk to MySQL with an admin password and create the database if it doesn't exist yet. So we want to make it super easy to bootstrap a new service. So I don't want to have to remember when I start a service, if it needs a database, I don't want to remember to have to go create the database. So mfrun will do it for us. The service itself cannot create the database, by the way, because the service will not have admin access to MySQL. That's very important, right? You don't want, the user that you use for MySQL in your service to be an admin. You want to give only permissions to modify its own database. So this needs to be done outside and before you start the service. The service itself, when it starts, it can do the migrations, and it does. But the database creation needs to happen outside with an admin password to MySQL. So that's users here. Once again, this is a pretty standard, I'm going to look at V1, pretty standard app in Flask terms. It imports the authentication stuff from the common package. There are some utilities that I also put in the common package because they're used in all the services. The basic auth, so checking for username and password, that's not a common, it doesn't belong in common because the only service that can check a password is this one. So that's here. So this is a guide. This is using the Flask HTTP auth extension. And right here you can see that this is how it's done. It's pretty standard. So this is copy pasted from the application, from last year. So we have the model, standard SQL Alchemy stuff. We have, these are these two, the from dict and to dict. These are the ones that convert a model to a representation for the API. So here there's one interesting aspect. There's something that we lose by going to this structure with microservices. Typically you use URL4 to build URLs, and in the original app from last year, I used URL4 to generate the links. So basically, this will be the hypermedia portion of the REST API. You will use URL4 to build links, right? So if you get a user, you will get a link to get the user messages. Well, turns out now the user messages are in a different service, so URL4 doesn't know nothing about it, right? So you can't use URL4, unfortunately, to build URLs, at least not all of them. So there's two options. You can say, okay, I'm going to forget about hypermedia. Nobody cares anyway, right? That's one option. And then the other option is that you build the links by hand, unfortunately. So to keep things compatible, since the previous version had hypermedia links, I decided to keep them. So those links are built like that, right? Because it's a different service. In a very, if you have a very big distributed service, you could have a service that knows how to build URLs. That will be one way, right? And then services can register their endpoints with this one service that knows how to build URLs. You could do that, for example. So this one and also the tokens one, right? Those are going to be built by hand in this service. By doing this, I saved myself from having to hard code the URLs in the UI. I didn't want to change the UI, so that's basically that's the reason I decided to go this way. But it's not ideal. It's a problem. It's one of the cons, I guess, where you go to a system built this way. Other than that, this is a pretty standard Flask application. To save time during the break, I built the container. That takes a minute or so. So I built it. So to do it, you will go to Flask users in the VM. You will do get checkout 1, which I did already, and then you will do build.sh, which I did already, and that's why it's fast. And then you will say mfrun users. And that's going to run one of the users service. The database will be created at the time you run it for the first time, and then you will have users running. There you go. And this is V1 of the user service. Any questions? So if you were to look at, if you run the application in the browser, now you're going to see that /API/users does not return a 404 anymore, but /API/messages, which the UI will also try to invoke, will, because we don't have that yet, and tokens if you try to log in as well. Okay, so now if I wanted to use the user service, I need to be able to give out tokens. So I decided that would be the next service to deploy. And little by little, we're growing this back into the original application, but implemented in this format. So for tokens, there was 2 things you can do. You can get a token, and then you can revoke a token. This is in the original app. I decided at the time I was about to do this. I didn't know exactly how I would do the revocation part, so I decided to put that off. So I know I need to do it, but I want to see something going first, and then think about what's the best way to do it. So I didn't implement that yet in V1. So this one then has only one endpoint, /API tokens. You send a post request with username and password, and then you get back a token. That's it. To verify the username and password, as I said, tokens sends a request to the user service. So let's take a look how this is the first time we have 2 services communicating. So let's take a look at that. So this is going to be in tokens. Tokens is a very short service also, because it's got only one, that one endpoint. So the basic auth is this is the way we are going to receive username and password, and the way we verify it is by sending a request to API users me. And we send the auth, we pass it through to the user's service. And if that comes back with anything that is not a 200, we say no. And if we get a success, we basically take the content of that request, the response, which is going to be information about the user, and we put it in the G for Flask, so that the endpoint can have access to it. Does that make sense? Now, note that here I'm using a relative URL. So you may think that this requests is requests, but it's not. I have a wrapper for requests that I called originally requests. This is coming from the common package. So this is the module. There's a module called requests that uses the same interface as the Python requests, but it has a couple of added features that are specific to this project. If you send a relative URL, like this one, / something, without sending a host name or a port, then it'll assume that you're talking to yourself, to the load balancer, so something that's load balanced in the same system. So it'll prepend the load balancer address, which is in an environment variable. As we said, we configure everything in an environment variable. mfrun, when it starts a container, it will set the LB environment variable to point to HAProxy, and all services have it. So you can be sure that that's available to you. So the request module in the common package will do that if you don't send a host name. The second thing that it will do is it'll configure requests to do retries. I mentioned that that's very important. Sometimes there are glitches, things happen when you have so many pieces moving, there are sometimes unavoidable, little downtimes. When things upgrade, for example, sometimes you have a very short interruption. So this, the retries, you don't even need to ask for them. You get retries. I'm not going to show you the implementation. The implementation is very simple. You can go look it up in the common package. I want to save time to show you more interesting stuff. If not, we're not going to have time. But if you have questions later, please ask me anytime. I'll be happy to explain anything you don't understand. So, and then the endpoint, basically, this invokes the auth part that's above. And this is a post request that it's going to invoke generate token, which is also in the common package. And this is the function that generates a JWT token. And the contents of the token is going to be the user ID, which we already have in G after we passed authentication. Does that make sense? And that's it. We have another service. That's all it takes. So to deploy this, it's once again, and I also did this one to save time. So you're going to do git checkout 1, build, and then mfrun tokens. And at any time, you can run more than one, as you saw before. If you run 2, it's totally fine. Then you have double the bandwidth for that service. So there you go, tokens. So now we have the UI, users, tokens. We're still lacking messages. So now that's the next obvious move, is to add messages. So messages is going to be in many ways similar to users in that it uses a database as well. This is the summary from the original service. All the messages endpoints are here. And for this one, I found no reason not to implement exactly the same APIs, the same endpoints. So straight copy-paste of all of them from the big app into a small standalone Flask application. I think I didn't repeat this enough. For all these services, when I'm doing copy-paste, in every single one, I made mistakes. Every one. And I found those right away by running the tests. So you need tests. You need them before you attempt this. If you add them after, then it's kind of it's a dirty setup. You're gonna be you're gonna be predisposed to be nice how you write your test. You need to make sure that you have good test coverage for the original code before you migrate it, if you want to be successful. If not, you're gonna miss stuff. Another thing I can tell you, I typically, in terms of test coverage, for things that I want to make sure that I don't break, like my public open source packages, I try to go 100%, so test everything. I think 80% coverage is usually good. The corner cases are what's left, so you're probably okay with 80%. For this example, last year I think I had about 80% coverage, and I tried to keep 80% on all the services if you run the tests. So same structure as the user service, right? It's a service with a database. It's pretty much copy-paste of the big application. This service had some asynchronous action, right? I don't know if you remember, I showed you at the beginning that a message that you type could have markdown and it could have links. And both things they need some processing, right? The markdown needs to be rendered into HTML. And if you type any links, we went and grabbed the page and then scraped the title and description to show as an extra thing. So those were done asynchronously. That was the task of the Celery worker, if you remember from last year. Unfortunately, Celery is not a good match for this. And I explained this. The Flask service and Celery both run the same code. So if you change one, you're forced to change the other. And we're against coupled services now. We want to have the freedom to scale or upgrade services independently. So Celery promotes a coupled situation that it's not really beneficial. So I'm not going to use Celery anymore. Once again, I said this is too complicated, so I'm going to pass on this. I'm going to go back to synchronous in the beginning. I'm going to start small, just make it be slow, inefficient, but make it work, and then I'll look into how can I improve it and make it go back to asynchronous. So in the beginning, when you send a request to the post request to post a new message, it's going to be rendered right there. I'm not sure there's much new stuff to show in this service, in version 1 at least. Basically, this is in the model, this is when you create a new message. So here, this is the rendering, which I, after I copy-pasted the code from the original Flask, I had to put this back into asynchronous. The method expand links existed from before, but it was called from the Celery side. So I'm calling it here. The render markdown, this is the other one, the one that renders. This is called anytime there's an event handler on the SQL Alchemy column, when you set the message text, that invokes a handler that renders the markdown, and I kept that. Other than that, this is once again Flask standard stuff. So I'm going to go ahead and once again, this is all boring. I'm going to do it again. Build, which is fast because I pre-generated it, and then mfrun messages. So now this is running. Now we have all the components that we need for a first version that's everything. So I'm going to refresh, make sure I get the latest. I don't get any cached stuff, and well, we have it. If I type a link, clunky, slow, but it works. So now we need to find a replacement for Celery, right? You could use Celery if you wanted. You can consider the messages service plus its Celery workers, like one thing if you want. That would be acceptable. I think it's going to complicate upgrades and deployment, right? Because you will have to upgrade both. If you change the database, for example, which both will have to use, you have to upgrade both at the same time. I think it's doable because it's a contained problem, small. there's only two little things looking at that database. I decided to not go that route. So something that people, for some reason in the Python world, don't like is threads. They think they're bad, ugly, never use in Python. We're better than that. I kind of disagree with that. I think threads have a very useful purpose. So what I'm going to do is to do all this rendering in a background thread. So it's going to be an asynchronous request. When you send a post request to create a message, the route, the method that handles that route will start a thread, and then it'll say, okay, fine, 202. So I'm going to work on it. But basically, that's the code to say, I got this, but I'm not done. I'm going to do it on my own time. So it's going to respond with 202, and then start a thread that will do the work. In some cases, you may not want this asynchronous work to be in the same space as your API process. So you may want it somewhere else, so that it cannot affect the performance of your API listening. The part of the service that listens to requests. In that case, you can use multiprocessing. Just put it in its separate process, short-lived process. Or you can go all the way async. I mean, you can go if you're willing to drop Flask, you can go async IO if you want, or you can use any of the other async frameworks that Flask supports, like Eventlet or gEvent. Those are all good options, and it depends on the case which option you should go. So I'm going to use this opportunity to show you how you would work on a new feature on your local laptop and test it, without getting crazy with all this other stuff, the load balancer, all that stuff that you need to deal with. So I'm going to show you how to install the version 2 of Messages, which is the one that starts the background thread on your local laptop, and then you can test it locally by sending requests directly, so in isolation, right? So this is an independent service, so you should be able to test it by sending requests with curl or HTTP or Postman, whatever you use. Yeah, that should work. Oftentimes, you may also want to test it integrated with the rest of the system. So I'm going to show you how to hook up something running in your laptop to the load balancer running inside the VM. I'm sure you can guess how, because I showed you already how to do the big flag, right, the old flag. So it's going to be exactly like that. So I'm going to exit the VM. Now I'm on my laptop. Only have the admin package. So I'm going to clone I need the common package, and I need messages. So in admin, there is this mf bars. This contains a bunch of useful environment variables that configure a lot of things so that you can work with this system. So I'm going to source that. I can show you quickly. So it configures the name of the services. So mfrun uses this to know, what's going on, which services you're using. It also configures which services need a database. Also mfrun uses this. Which services are dependencies. It configures the pip so that you can pip install things from your local machine. And it also sets this Flask app so that I don't have to think about it. I can say Flask run, and it works. And I said, oh, I forgot to set the variable. So I never forget this way. So a bunch of things that basically configure the environment. So that's sourced. So now I can go in the common package, and I can say make will all. So this make will, by default, it will build the code that you have right there in your directory. If you say all, it will go look in the Git history, all the releases by looking at tags. So in this case, for this project, I had 3 versions. There's 0.1, 0.2, 1.3. So if you say all, it'll build all of them. And then all the versions will go in the folder, in this directory where you have all the wheels. And services may use one or the other, and eventually you probably tend to upgrade all of them to newer versions. But you may have some services that use an older version, and that's fine because we're building all the versions. So this is going to go find all the tags and build all of them. And it knows where to put them because that's one of the variables in mfvars. That's the wheelhouse variable. It's actually it's a sister directory to this one. So now we have wheels and we have three packages there ready to be installed with pip. Pip, if I say pip install this, it'll work because the environment variable configures this directory as a source for packages. So it's pretty handy. So now I can go to messages. I can do the standard stuff, make a virtual environment. I can activate, pip install requirements, usual stuff. And then after this, I can just run it. It's Flask. For me, it's very important to not alter, at least not much, the development workflow that we all love, right? I mean, that's part of what makes me like Flask so much. This is actually very convenient. So now I can say Flask run. And it's running. So this is running in isolation. I can send requests to this at localhost 5000, and I can test the hell out of it. It's just fine for testing. Okay? So I went through this, and first part of this, right? So we are at a point where we can test this locally. I think I forgot. Yeah, actually, I forgot to set version 2 here. We deployed 1, now we're going to do 2. So I'm going to switch to 2 and run version 2. Now, if you wanted to test this, for real, in interaction with all the remaining services, we can write entries in the service registry once again to point back to this guy running in the laptop. It's totally fine. I wrote a script that automates that, makes it very easy. It's called mfdev. There you go. So mfdev will write the entries in the registry. So if you say mfdev start messages, it'll do that. Now, before you do that, there's a bunch of environment variables that you need the service to know. So for example, you're going to send tokens to this service running in your laptop, and the service needs to know the signing key for those JWTs so that it can validate them. Right, so all those things are in the VM, in this Vagrant VM right now. So I created another script, it's called mfenv, that dumps, of course this, it goes without saying, you're going to do this only for development, right? You're not going to play with passwords, so happily in a production server. Never do this in a production server, right? This is for testing only. But mfenv will dump all those, variables that a service needs to the console, and then you can copy paste them and put them in a .env file. So let's do that. So I'm going to go back to admin. You can do vagrant SSH and put the command right there. So you can say mfenv. So it's going to go in the VM, run this, and then out. Please, there you go. So this is a bunch of things. You can see that there's how to find the service registry. It's this variable. How to find Redis. How to find the load balancer. The user session key. The JWT signing key. And then the database URLs for all the services that use databases. You will have to uncomment the one that you want to use if you want to use it. So this is all here, so I'm going to copy all this stuff, take it to messages, and create an .env file with all of that. So for databases, I can uncomment this one for messages, and then I will be connecting from my laptop into the MySQL database that's running in the VM, or I can opt to not put it and just let the service create the database on its own. So this service that's only for development will be running a SQLite database by default. That's the default. It'll be in your laptop, a file, and that will be the case if you make changes to the database. In that case, you will not be able to use the database in the service without upgrading it, and if you upgrade it, it may cause trouble to the other instances that you have there. So those are all options. So now I can say, now I have the environment, so I can say mfdev. I don't have it in the path here, so I have to go reach into the bin directory of the admin repository. Start messages. Before I apply that, I'm going to switch here. So it says OK, and it reminds me that I need some variables, right? And then it tells me, and this is a default, that there are arguments to mfdev if you want to change the port, all that you can do. But by default, it'll assume that it's your laptop at 5,000. So that there's the new entry. It just wrote the new entry. So now I'm going to say Flask run. And look what happens. Green. Okay? Oh, look at that. I forgot to create the database. Sorry about that. So this is telling me there's no database. So I need to say Flask db upgrade. Because I'm not using the database in the VM now. I didn't configure that. I need a database here. This is going to look for a SQLite database. So upgrade database. Oh, sorry. And now run. And now it should be OK. And it should start receiving traffic. There you go. Now, you see that there's another one, right? So these two are both receiving traffic. But mfdev registers this entry with a weight of 256. So HAProxy can give different weights to different instances. So mfdev, you can look how I'm doing it. It's basically writing the address of the service with an extra weight argument. And that will make it much more likely to get traffic. If this is inconvenient, if you want to make sure that you only get traffic on your laptop, then you can kill the container, the other container, and that will be, that will make you 100% the owner of this service when you test. So, basically, that's the development workflow. As you see, it doesn't change much from what you normally do, and I think that was, for me, that's very important. Any questions about this? So I'm going to skip showing you the thread stuff because it doesn't really add much to I think the topic of this class. So you're welcome to review that. But we can deploy that now for real. So I can say here mfdev stop messages. That will remove that dev entry once I'm done testing. And then I can go back into the VM. And messages, I'm going to check out version, this is version 2. I need to build it. It's going to take a little bit. And then once it builds, I can go ahead and run it. And it's going to be interesting because now we can't just run it, right? We need to upgrade. We have an existing version of this. We have version 1 already running, and we are going to upgrade it to version 2. So let's wait for that to finish and try that. Right. almost there. So this MF upgrade script, the bash script that does the rolling updates, I created a different, I showed you earlier that you can say MF upgrade roll, and then it goes through the motions of starting one, killing one, starting another one, killing another one, and so on. So that's one way to do it. If you're courageous and you're sure that the new version will be great, then you can go ahead and do that. Sometimes you're not so sure. So another modality that I put in this MF upgrade script is to do a little test. And this by having everything load balanced, all these, the creative ways to start services, they're made possible because the load balancer makes all of this super easy. I'm going to say MF upgrade try messages. So what this is going to do is it's going to start the V2, and it's going to start showing me logs. These are logs specific to this service. You can see now we have V1 and V2. They're running, and these are receiving 50% each of the traffic right now. So you can start looking at this. If you see any problems, then you can immediately Control-C this and say MF upgrade abort. And what this is going to do is just kill V2. And you're done. Safe. Okay? Now, on the other side, if you're seeing that it's looking good, then you can say MF upgrade roll. You don't even need to say which service because there's a pending upgrade. The script knows. It saves a file with all that information. If you say MF upgrade roll, it's going to continue that rolling upgrade motions that I showed you before. So it knows that there's already one that started, so it's going to do the rest after you confirm that the service is running well. In this case, we had only one, so all it needs to do now is kill the V1. So all this happened while the service was running, so it was responsive to all clients. Any questions about this? I'm not sure if you're all asleep, or I'm so great that you understand everything, and yeah, there are absolutely no questions. I'd like to believe that. So, okay, we have 20 minutes. So the next thing that I did was to implement the token revocation. So for that, remember I told you that it was highly inconvenient to have services verify tokens with a token service, and that's why we migrated to JWTs. Okay, there's a problem. The problem with JWTs is that you don't have to talk to the token service to verify them. So if they're revoked, how do you know? You're not talking to anyone. And if a token is revoked, you somehow need to know. So the solution for that is, unfortunately, to create a database not of tokens, but of only revoked tokens. And the logic that you need to convince yourself that this is not as bad, because looking up a revoked token is going to be much faster than looking up all the tokens every single time, right? The revoked tokens are going to be a small percentage of all the tokens, so this database is going to be small. In addition to that, tokens expire. JWTs have an expiration, so you need to keep them on the revoked token database only until they expire, and then they can go away. So your revoked token database is going to be typically small, and doing searches on that database, it's going to be much faster. And maybe you can allow yourself to cache those searches if you are not paranoid, if you don't mind maybe caching a revoked token check for 1 minute, for example. So if you get queries about the same token during a period of 1 minute, you can use cached information. And then if the token gets revoked within that minute, you'll find out in a minute. So you can do all those things to minimize the toll on all these requests inter-service for authentication related purposes. So we had the post request to request the token, and now we need to check if a token is revoked or not. That's going to be a GET request and the same endpoint, so API tokens. And then we need a way to revoke a token, and that's we had that in the original app. This is the one that I didn't implement in the first release of tokens. So that's going to be the delete request, and you pass the token in the headers of the request. So we need to implement these two. So what I'm going to show you, I think the only interesting thing about this in version 2, actually I'm going to show you the diff. So this is version 2. So we added the endpoint to revoke the token, right? And all this is doing is just writing the revoke token in a database. And what did I do here? Instead of creating a MySQL database for this, since this is you want this to be super quick, right? You don't want all the weight of a full MySQL database. All you need is to find this entry, see if it's in that list or not. In addition, as I said before, these entries are have an expiration associated with them. You want to keep them only while the token is valid, but then you want to remove them. So the etcd, the service registry that we're using, has the ability to store things with an expiration. So I said, well, okay, I could use a different portion. On that hierarchical structure, we have /services for the service registry. Let's use /revoke tokens to hold a list of revoked tokens. That's what I did. I used this Python etcd client library, the same one that I'm using to do the registration in the common package. And any token that gets revoked, I write it to that place in etcd, and I extract the TTL. This is the time to live, the expiration, when it expires. So I get the expiration from the token. If you recall, when we get a token and it passes validation, we put it on the G variable. So from there, I can get the expiration. This is part of the standard. All JWTs have, well, actually, if your token expires, then you should have an EXP item in the claims portion of your token. So I look at that and then calculate how long that token has remaining of its life, plus 5 seconds for safety. And then I set the TTL on the etcd. So etcd, it's going to remove expired tokens from me, for me, without me doing anything. It does it for me. Does that make sense? And then in the common, verifying a token is in the common package. So I had to add that to the common package. So here in the verify token function, there's a new function, is token revoked, and that's now part of the validation. And I disable it for testing, of course. But if when I verify token, in addition to checking that the signature is valid, I check the token, the revoked token list. And as I mentioned before, I wanted to try this cache idea. So I added this TTL cache, which this is from a package called Cache Tools. It's an open source package. So basically, for 1 minute, I'm not going to repeat a query for a token that I get. If I get it again during that minute, I'm going to use a cached answer if it was revoked or not. And then after that minute, I'm going to ask again. So that's how this works. Now this is going to be the common package version 0.2. And all the services we have so far are on version 0.1. So we can release this, and then we need to do some new deployments. We need to upgrade users and messages to use this so that they can check token revocations. And you can do it at any time. And until you do, you're not going to have, you can deploy this functionality and have the services not use it. That's totally fine, right? That's the whole idea with micro deployments, right? As you have a little piece of a big feature, you just throw it over the fence, deploy it, and it sits there until someone starts using it. So, of course, before we start thinking about upgrading, all those services, we need to deploy this functionality. So we're going to go to tokens and get version 2, build it and deploy it. Oh, that was quick. What a nice surprise. So MF upgrade, I can say roll tokens. And that's going to upgrade tokens to V2. So now we have the functionality, and now we need to bump the common package version in the requirements file for users and messages to 0.2, and then deploy those independently at any time, and then that will basically implement this feature that spans all these services. So in the spirit of saving time, I'm not going to, building these packages take a minute or two each, so I'm not going to do it. But you should do users, send it to version 2, MF upgrade roll users after you build it, and then messages to version, we are on 2, we need to send it to 3. And if you look at the diff in GitHub for these two versions, version 2 of users and 3 of messages, the only change is a change in the requirements. That's it. So this is the final one. So the only thing that we're missing now is the WebSocket portion, right? The socket IO part. And this is the most challenging one because it affects pretty much the whole system. So I'm not going to make it. I have like 10 minutes. Hopefully they don't kick me out if I run a few minutes late. Fingers crossed. So these are, I don't know if you remember from the original app. Socket.io is a protocol that's based on events instead of requests like HTTP. So this can work over WebSocket, or it can work over long polling. And the Socket.io protocol adapts itself. It finds the best mechanism to do this. If the client supports WebSocket, it'll do that. And if not, it'll go with long polling, which works anywhere. So there are 3 events in the server. There was one that the UI sends to ping users. But basically, this says this user is still active, and that will keep it in that list on the right as an online user. And then when you post a message, the client sends the post message event. And when a client goes away, the Socket.io protocol itself will send a disconnect. And then that's when we are going to mark that user as offline. And that will make it go away from that list on the right. And then, so that's on the server. And then on the other side, Socket.io is bidirectional. So the server can do server push and send stuff to the client. And one that basically updates anything that changes, it's called updated model. And that could have a new user, a new or changed user, or a new or changed message. And then the UI doing JavaScript will know how to get that, whatever it's in the DOM, updated. And this is not the right conference for that, but if you are interested in how I do that, I'm more than happy to tell you. But basically that didn't change from last year. That's the same mechanism. And it's implemented with Backbone, by the way, Backbone.js. Something that I realized that I missed last year, this is a bug in the application. When I was doing all this work, I found this bug. If you post a message and your token has expired, if you post it through Socket.io, the server will receive it. It'll try to validate the token. It'll fail, and then it says, "Okay," and nothing happens. So then the client doesn't find out that it needs a new token. So I added one more message that the server can send to the client, expired token. So if the client sends an expired token, then the server will push a notification to let the client know that it needs to do something to get a new token. And in this implementation, I send the user to the login screen so that it can log in again. Probably in a production app, you will not do that. You will have a mechanism to renew the token. So I didn't know where to begin. There are so many things that you need to change to implement WebSocket in an application that doesn't have it. Especially because now we have all these 4 services, and where do you start? So I made a list. I made 4 lists actually of things that need to change. So of course for the Socket.io service we need to make it right. That one doesn't exist. But that's actually easy because we can copy paste from the old app. But then the common package needs one little piece with the load balancer. The Socket.io service is stateful. So if you have, let's say you have 3 instances of Socket.io on the server, you need to make sure that the load balancer sends the events from one client always to the same instance, because that's the instance that keeps track of that user. So this is a stateful service. Remember I told you this is a big no-no. Well, we have no choice because that's the way things are. I'll tell you how to handle that. But you have to account for that. So HA proxy as well as Nginx, they all, load balancer have a configuration item where you say, it's called different names, but it's typically called sticky sessions. That means that when repeated requests come from the same client, the load balancer, via some sort of algorithm, it remembers which of the instances received that the first request, and it keeps sending those requests from the same client to the same instance. That's called sticky sessions, the generic name. So HA proxy supports that. And the container that I'm using that hosts HA proxy also supports that, but I didn't implement it up until this point. So that needs to be added. So that's going to go in the common package. The UI service, when users come online or offline, it needs to tell the UI, it needs to push a message to say, hey, you need to update the status of this user. This user didn't exist and now it's online, or this user went away. Now you need to remove it from the list. So that's done through the message queue. The user service, it's the only service that knows when a user comes online or offline. So it'll push to the message queue the updated model event, and then the Socket.io service will pick it up from the queue and send it to the client over WebSocket or long polling. So that's users. Messages, same thing. When a new message comes, or when we have this asynchronous message rendering, initially we're going to show the message with the markdown, and then we're going to go in a background thread to go do the scraping of those URLs that might be in the message. When those URLs are back and we have that content, we need to re-render that message in the client. We're doing it in 2 steps because we want to show the message immediately, and then when we have the remaining information, we expand it. So when that happens, once again, it needs to put a message in the message queue. And then the UI needs to know that now it needs to connect via socket IO versus REST, which it did before. So we need to make all those changes. We need to make them in a way that nothing breaks ever, right? So at all times, you're going to have users running this and chatting, and you have to somehow figure out how to do this. So for the socket IO service, it's going to be a very simple service. So it's going to have only socket IO events. It's not going to have any REST and any HTTP endpoints. It doesn't have anything like that. It's so far removed from HTTP that at some point I consider I don't even need Flask for this. Right? You don't really. Except that Flask has a user session, and so the Socket IO, there are two packages for Socket IO, both are mine. There's a framework agnostic package called Python Socket IO that works for any framework. And then I created a Flask Socket IO package on top that adds some niceties and makes it look a little bit more friendly to, if you're using Flask. And one of the things that I added in the Flask package is support for the user session in the Socket IO events. So I decided to stick with Flask just for that reason. I wanted to have access to the user session. So I decided to basically keep Flask, but still I wanted to go async. And the reason that this needs to be an asynchronous service is that each WebSocket connection will take one worker, one dedicated worker. It's a long-term connection, unlike HTTP where you connect, do the thing, and then the connection breaks. So this is going to stay on for as long as the client is connected. So if you have one worker, you can take only one client, unless you go async, in which case you can have thousands, basically. So if you want to understand why all this logic of going async when we're using WebSocket, I'm doing a talk on Sunday about this. So you're invited to that. But basically, you have kind of no choice when you're working with this type of WebSocket or long polling, this long-term connection type stuff. So now you need to start thinking, how to coordinate, right? So we know that the Socket IO service will have to send mark users as online or offline, right, as they connect or disconnect. Now the Socket IO service will be the one that knows when a socket, when a client comes online or offline. That's the service that will receive the notifications. So we need to add endpoints in the user service to basically mark a user as online or offline. So 2 new requests. So we're going to use put and delete on this /me endpoint. So put will set the user online, and delete will set it offline. And then Socket IO will send these requests to, when it gets the notification, it'll internally talk to users to update the user state. So the Socket IO service, let's take a look. It's actually fairly simple. So once again, there's an app.py, and it's actually very short. It's all copy pasted. So we have the three. So we have ping user, post message, and disconnect. So disconnect is triggered automatically by the Socket IO server. So for these two, the client will initiate, right? It'll send the event and it'll pass a token, right? It has the token, so it'll send it. Now for disconnect, we don't have, but disconnect basically comes from the framework itself, so we're not going to get any arguments. I still needed a token because I need to send a request to users, right, to mark the user offline. So this is the reason why the user session in Flask was useful. Anytime I get a token in any of these two client-initiated events, I save the token in the user session. And that's how, when I get a disconnect, I have the token to mark the user offline. And that's the only reason why, in this case, I decided to go with Flask. if I wanted to implement the user session on my own, I could have gone with async IO, whatever. It doesn't really matter. So we can go ahead and deploy this Socket IO. So once you have the Socket IO servers ready, you can just throw it over the fence and deploy it. Nobody will use it yet, but you can deploy it. So I think this should be built. Yeah. So mfrun. So mfrun I use for the first time, right? mf upgrade is when you already have it. So mfrun Socket IO, and that's going to run. Nobody will use it yet. So the way you coordinate, so you want to make sure that this new service is not used until all the parts, in other services are implemented. So you want to make sure that users is able to push updates to the message queue, and you want to make sure messages is also able to push to the message queue. Once you have those two pieces, then you can say, okay, I'm going to update the UI to connect via Socket IO. So we need to upgrade these three services, right? They all have parts of this feature, but you need to, we need to find the correct order to deploy these so that the application always runs, right? So usually you're going to be deploying, pretty common to deploy features in dark mode, right? They're going to be there, but nobody will be using them. So we're going to have users, it's going to be pushing changes to Socket IO, but there's not going to be any Socket IO clients to listen to them yet, right? But that's the correct way, right? If you deploy the UI first, then you're going to be missing notifications. You want to make sure that the notifications are in place before you start using Socket IO, right? So you have to think very carefully about the order and test it on a staging server. Make sure that really things don't go down while you do the upgrades. So basically, that's the. I think this is a very good example of how to carefully think about how to deploy, complex updates that require, multiple services. The opposite of this, which I've seen, and it's really awful, is when if you have, these three services that, or actually four, just shut everything down, upgrade everything, and then everything back up. But you have downtime, right? So, not good. This is, in my opinion, this is better. You can still reserve the option to use downtime when you have something really complicated. But this is more exciting for me. Think about doing this in terms of keeping everything going, right? Like the big guys do, right? They really, sometimes they go down, right? But it's actually when they never expect it, not when they do an upgrade. So I'm going to let you do these upgrades on your VMs at your own time. There's really, if you do it in this order, then you're going to have the end product. After you do this, you're going to have the one that you get when you deploy the VM for the first time. And this completes the project. So I'm 8 minutes late already. So very quickly, I wanted to tell you that even though I went, I went with a homegrown solution for deploying this, which is totally valid. I will use it myself. I really like it because of its simplicity. It's totally fine. You could take this application and deploy it on Kubernetes, for example. And I was wondering if it would be easy or not to do it. And I went and created all the scripts to do it, and I didn't have to change a single line of code. So if you go on the admin repository, install/Kubernetes, you have all the scripts, and you can deploy this on a Kubernetes cluster. Things that you get for free when you use Kubernetes, secrets are not handled through the environment. Kubernetes has a subsystem for storing secrets, and I'm using it in these scripts, handle secrets the correct way as far as Kubernetes go. And then the way you register services on the load balancer is simplified because Kubernetes gives you a DNS name for each service. So, for example, HTTP users, it's going to be the load balanced user service. So, you always talk to users on that URL. So, and then you do the scaling through the Kubernetes calls replicas. So you can set the replica count on each service, and that will create more instances instead of using the mfrun homegrown thing that I was using. But the containers are all totally compatible. I didn't need to change anything because inside the container there's no assumptions made. Okay. So another option that you may have is to go with the container service in AWS. Right. This is actually the same as having a Docker running on a VM. So no problem there. As a benefit, you have access to all the services in AWS if you like that. So instead of using Redis for the message queue, you could use SQS. You can start migrating to you can start RDS database if you want instead of deploying your own MySQL. So you have all those options, and they're going to be nicely integrated with the service. But once again, the code is completely independent because all the configuration goes through environment variables. So and of course, if you've used AWS, it's a headache to set up roles and stuff. So that's of course we don't have that on this little solution that I built, with Bash scripts. But when you deploy to AWS, you're gonna have to have security, in mind, and you have to set up your security groups accordingly. You can go serverless. This is another option. So this is what I do at work. So I have some experience with using Lambda and API gateway. It's a completely different paradigm. The idea is that not that there's no server, but that you don't have to run a server, right? You push the code to AWS Lambda and then configure your endpoints in API gateway, and then AWS runs a server for you. And it does it how it sees fit. So it will start a server when there's some traffic. If you get a lot of traffic, suddenly it'll start more instances. So auto scales, all automatic. You don't have to create a load balancer. You don't have to create a service registry. Nothing, right? AWS will do it for you, and it'll charge you per usage. So each request gets you have to pay for each request. So it's really nice, but yeah, it's very different. In particular for WSGI applications, we're used to writing servers, right, in WSGI. And here you need to write a function that AWS can call. There's no server. So GUnicorn doesn't apply, for example, or UWSGI, none of that. You just need to provide the code. Now, if you know how WSGI is implemented, WSGI is a callable, right? It's a function that you call. So there are tools that convert a WSGI server into a function. And the most popular one is called Zappa. It's open source. It's pretty good. I also made an attempt to a tool of this kind that's called Slam that basically does the same thing, but it does it in a slightly different way to Zappa. So you're welcome to try both and see which one you like best. And then one of the problems I see, since you have no server, there's no way to establish long-term connections. So WebSocket is a no-go. You can't have a server running for a long time because you pay for the time that your function runs. So if it runs forever, all the functions have a timeout, so it's not going to run forever. So there's no way to keep a connection alive for a long time. So in this case, if I had to do this with Lambda, I will deploy the 4 services that are not WebSocket as Lambda services, and then I will deploy the only WebSocket service, in an EC2 or ECS container. The other thing that I noticed, it's a constant pain for us. It's that compared to something that you deploy normally, serverless is slow. So all the requests going through API gateway and then into the Lambda, AWS needs to start a server when you don't have constant traffic. So all those things add up, and the response times are not that great. They're not awful either. It's something that you can work with, but it's a little bit slower than what you would like most times. Finally, another thing that you can do is if you don't like any of this Docker nonsense, right? You can just deploy processes, and that's totally fine. All the stuff that I did today can be deployed as a regular process the old way, and it's totally fine. So etcd, HAProxy, confd, MySQL, Redis. So all those base services, they can run as a regular process. They don't have to run under Docker. You're going to have trouble scaling them, right? Because then you're going to have to assign ports, right? Now you're running in a host, and you have to manage which ports you assign to which services. In particular, for your own, the application services, you're going to have to, if you want to scale up, you're going to have to find an empty, an available port to run the new instance. And then, that's Docker does that for us. So it's really nice. So I created, you don't have to read all this right now, we don't have time, but I created a long list of ideas to improve the system if you want to play with it and get more used to this idea of running microservices. There's a bunch of things all over the place that you can attempt. So going from improving the token service to having a highly available databases. Somewhere in there, I don't think I mentioned this. Now that we've lost the ability to do joins in a relational database, using a relational database, it's not really that useful compared to going NoSQL. If you've seen my talks, I really like relational, right? I'm old school. I like relational, but if you don't have your joins, what's the point, right? So one of the assignments here is you could go try either Mongo, or if you're on AWS, you can try Dynamo, one of those. So anyway, Chaos Monkey is another thing that could be interesting. Now that you have this, you can write a script that randomly kills services and then enjoy when you see that the thing doesn't go down. So a number of things you can try. They're very ordered from easy to insanely complex, I guess. So this is the order. So anyway, okay. It's late, but I'm sorry. So I'm done. I'm going to take questions if they let me. And once again, that's the link for you to provide feedback about this class. Well, that's it. Thank you for coming. So any last-minute questions? There's one. Yes.
Yeah, I heard that you say that it is good as infrastructure architecture to have a load balancer for each service or app, right?
Yes. I didn't say exactly that. You can use one load balancer that load balances all the services, right? The load balancers, you can configure different groups of scalable services. That's actually what I did here. There's only one HAProxy, and then it finds by the URL that you use which of the services is basically the request going to. And then it'll load balance among only those instances, the ones that belong to a single service. Does that make sense? Any other questions? Going once? Yeah. The supporting scripts. Yes. Right. So That's a good point. I could have gone more into trying to avoid duplication. Now, if you look carefully, you're going to see that the build scripts, for Docker, sometimes they need to be different. They're not identical. They're not exact copies. So, for example, a service with a database will build in one way. A service without a database will build in a different way. So it's not always an identical copy. So that's one reason why I decided to keep them, to have different copies in every service. But you could, in the same way I implemented the common package for code, you can implement the same thing for the scripting, all the tooling around, getting a service deployed. You could totally build a common repository for that. The reason I didn't want to put everything in a single repository is that when you're doing this for real, if you're in a team of people working, it's really inconvenient to have everything in the single repository, and also dangerous because you're tempted. That sort of promotes the the coupling that we don't want for this type of architecture. So I decided to go with the 7 repositories just for that. I agree that for a little test, it's going to be convenient, but I think it promotes a healthy decision when you do things for real on a real project. Yep. Any other questions? Okay, looks like we're done. Thank you.